Today we're doing section 9.8, power series. The definition of a power series. If x is a variable, then an infinite series of the form an times x to the n equals that is called a power series. More generally, the infinite series of the form where we have an times x minus c to the n is called a power series centered at c, where c is a constant. And you may also see it called a power series generated at c. A power series function of x in the domain of the power series is defined as the set of all x for which the power series converges. So let's look at theorem 9.20, convergence of a power series. For a series centered at C, precisely one of the following is true. The series converges at only C. There exists a real number r greater than 0 such that the series converges absolutely for the absolute value of x minus c is less than r and diverges for x minus c is greater than r. The series converges absolutely for all x. The number r is the radius of convergence of the power series. If the series converges only at c, the radius of convergence is 0. R equals 0. And if the series converges for all x, the radius of convergence is r equals infinity. The set of all values of x for which the power series converges is the interval of convergence of the power series. So the radius of convergence is less work, and this is how far from the center can I go to still get convergence. The interval of convergence is actually more work, and this is for what values of x does it converge. Make sure that you read the questions because you don't want to have to do more work than you want to. Also, the only way to do this is by using the ratio test because you need that absolute value. So let's go ahead and look at example 1. Finding the radius of convergence. Find the radius of convergence of the series n factorial times x to the n. So always start with the ratio test. So for these, we're always starting with the ratio test. So I need to find the limit as n approaches infinity of the absolute value of n plus 1 factorial times x to the n plus 1 all over n factorial times x to the n. So remember that we can cancel stuff out. N plus 1 factorial and n factorial can cancel out, and x to the n plus 1 and x to the n can also cancel out. So this would become the limit as n approaches infinity of the absolute value of n plus 1 times x. As I approach infinity, this limit equals infinity, which is greater than 1. So this diverges by the ratio test. So the radius of convergence is 0. The series converges to 1 at x equals 0, but diverges everywhere else. So this is centered at x equals 0, and it has to equal at the center, so the radius is 0, because as soon as you leave the center, it diverges. Example 2, find the radius of convergence of the series 3 times x minus 2 to the n. So again, we start with our ratio test. So the limit as n approaches infinity of the absolute value of 3 times x minus 2 to the n plus 1 all over 3 times x minus 2 to the n. This simplifies to the limit as n approaches infinity of the absolute value of x minus 2. And this would just equal the absolute value of x minus 2. Now, by the ratio test, for this to converge, we need to set this less than 1. So you always set your absolute value to find the radius of convergence to less than 1, okay? And you can go 1, so from here, what we would do is you can either visualize it, or I like to, a lot of times, actually solve this out. And you'd have -1 is less than x minus 2, which is less than 1. You go ahead and add 2 to all sides, and you get 1 is less than x, which is less than 3. Here, your center is at 2, because we get our center from here. This is how we get our center. Our center is at 2, which means if my center is at 2, I go 1 to the right and 1 to the left. So my radius of convergence is 1. Let's go ahead and look at example 3. Find the radius of convergence of the series -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. So here, we need to use the ratio test again. That's always what you do. So we would have the absolute value of x to the 2n plus 3 all over 2n plus 3 factorial times 2n plus 1 factorial all over x to the 2n plus 1. This equals the limit as n approaches infinity. We want to simplify some things. So x to the 2n plus 3 over x to the 2n plus 1, that simplifies to x squared. All over 2n plus 3 times 2n plus 2, if we were to cancel out our factorials. Because this one would be 1 times 2 times 3 all the way to 2n plus 1 times 2n plus 2 times 2n plus 3. Whereas in the numerator, we'd have 1 times 2 times 3 all the way up to 2n plus 1. And our 2n plus 1s would cancel out. This limit here, as n approaches infinity, I would get 0, which is less than 1. So the radius of convergence here is infinity because we have a true statement. So if it's a true statement, so 0 is less than 1 is a true statement, our radius of convergence would be infinity. The series converges everywhere else. So let's go ahead and find the interval of convergence for a couple of series. So you have to do the same thing. You have to find the, use the ratio test and go through and find that interval. But then you have to test the endpoints to see if they're included or not included. So we're going to start with our ratio test. So we have the limit as n approaches infinity of the absolute value of x to the n plus 1 all over n plus 1 times n over x to the n. This is the limit as n approaches infinity of the absolute value of n over n plus 1. Neither of those can cancel, but this would then become x when I subtract n from the numerator. So times x That limit would equal the absolute value of x, and we always have it less than 1. Okay, so this means that my series x to the n over n converges absolutely when -1 is less than x, which is less than 1, which we get from our absolute value, because these mean the same thing. Okay, so now what we need to do is we need to take those endpoints and plug them in for x. And we need to check to see if our ends converge or diverge using some tests that we already know. Okay, so we're first going to start at x equals 1. So when I plug 1 in for x, I get 1 over n. And this is a divergent p-test, or divergent p-series, because p equals 1, which is greater than or equal to 1, so it diverges. So that means we cannot include 1 in our interval of convergence. And now we have to check at x equals -1. So that means I plug in -1 into my x. So I would have the series -1 to the n over n. And this converges conditionally by the alternating series test. So that means we would include this in our interval of convergence. So the interval of convergence is -1 is less than or equal to x, which is less than 1. Let's find the interval of convergence for example 5 with the series -1 to the n times x plus 1 to the n all over 2 to the n. So again, we start with the ratio test. And we would have x plus 1 to the n plus 1 all over 2 to the n plus 1 times 2 to the n all over x plus 1 to the n. Now remember, you can ignore the alternating part since we're taking the absolute value. When we simplify our exponents, we would have the limit as n approaches infinity of the absolute value of x plus 1 all over 2. This equals the absolute value of x plus 1 all over 2, which we need to set less than 1. So we know that our series converges absolutely when the absolute value of x plus 1 is less than 2. So I just multiply both sides by 2 here. Okay, now what you would need to do is we need to find our endpoints. So this, when you take and have -2 is less than x plus 1, which is less than 2, we would end up getting -3 is less than x, which is less than 1. And we need to plug in our endpoints of our interval into our original series to find out if our endpoints converge or diverge. So at x equals -3, when I plug -3 into my x values up here, I get the series n equals 1 to infinity of -1 to the 2n. And that is always even. So our exponent will always be even. And when we have an even exponent, that means we'll always have positive. So our limit won't equal 0. So you can either use the geometric series test or nth term test, and it diverges. So diverges by geometric series test or nth term test. So that means we would not include -3. And now we need to check at x equals 1. And when I plug 1 in to x up here, I end up getting -1 to the n. And this also diverges by the geometric or nth term test. So the interval of convergence is -3 to 1, not including -3 and 1. And remember, you can't use the alternating series test because it only tests for convergence. It doesn't test for divergence. And if I were to look at this, since my center here is at -1, my radius of convergence, if I needed to also state that, would be 2. Let's look at example 6, finding the interval of convergence for the series x to the n over n squared. So again, we have to start with the ratio test. So we'd have the absolute value of x to the n plus 1 all over n plus 1 squared times n squared over x to the n. This would equal the limit as n approaches infinity of the absolute value of n squared all over n plus 1 squared times x. Here, when I multiply this out, I get n squared plus 2n plus 1. When I take the limit as I approach infinity, this would be 1. So this limit would just be the absolute value of x, and then we would set this less than 1. So that means that my interval of convergence it converges absolutely from -1 to 1. So now we need to go ahead and check our endpoints. So we need to check at x equals -1. So that's when I plug -1 into my original function, or original series, I should say. And I would get -1 to the n all over n squared. And this converges by the alternating series test. That means we would include -1, and then we need to check at x equals 1. So I go back up here, I plug 1 in, I get 1 over n squared, and that's a convergent p-series. Because p equals 2, which is greater than 1. So I'd also include -1, positive 1. So the interval of convergence is from -1 to 1 inclusive. Let's go ahead and look at a quick quiz. What are the values of x for which the series x plus 3 to the n all over the square root of 2n converges? That is circled because the notes might have the square root of n, but I think we fixed them from previous years. So this means you would need to find the interval of convergence. So take a minute, pause the video, and go ahead and find that interval of convergence. And hopefully you found A as your interval of convergence. If you have questions about that, feel free to ask me in class. So theorem 9.21, properties of functions defined by power series. If the function given by the following series has a radius of convergence r is greater than 0, then on the interval c minus r to c plus r, f is differentiable and therefore continuous. Moreover, the derivative and antiderivative of f are as follows. For 1, f prime of x would be the derivative of each individual term. The antiderivative of f of x would be the antiderivative of each individual term. The radius of convergence of the series is obtained by differentiating or integrating a power series in the same as that of the original power series. The interval of convergence, however, may differ as a result of the behavior of the endpoints. Let's look at example 7 to find the interval of convergence for f prime, and the integral of f of x when we're given the function of the series x to the n over n. This is from example 4. So we already know the interval of convergence for f. So the interval of convergence for my series is -1 to 1, including that -1. Now for f prime, that means we would multiply by that exponent and then subtract 1, means the n's would cancel. So that would just be x to the n minus 1, which is geometric, and it converges from -1 to 1. And that's because I would get from my radius of convergence, x, the absolute value of x is less than 1. And if I were to check my endpoints, I'd get -1 to the n minus 1 and then 1 to the n minus 1, and those would be divergent geometric. Now for my antiderivative, that would be x to the n plus 1 all over n times n plus 1, which has to converge on -1 to 1 based on our definition. Now we need to check at our endpoints. So let's check at x equals 1. When I plug 1 in there, I would get 1 over n times n plus 1, which converges by the comparison test to 1 over n squared. which is a convergent P series. Where P is equal to 2, which is greater than 1. And then let's go ahead and check that at x equals -1. So we would have -1 to the n plus 1 all over n times n plus 1, which converges absolutely by the alternating series test. So my integral converges from -1 to 1 inclusive.